Dear student, I hope that all are you well, and today on the power series solution of differential equation special functions, and we will discuss this chapter, and this is lecture 1. এই লেকচারটিতে আমরা যে বিষয়গুলো কভার করব, that topics are given here. First, introduction, then simple examples of solving differential equation. After that, validity of power series method, and then ordinary and singular points, and there are two types of singular points, and then we will discuss about types of singular points, then Frobenius-Fuchs theorem, and finally to test or some singularity points of some test singularity of some differential equation. So আমরা এখন enter our discussions. Here is the introduction. We already are familiar to solve ordinary differential equation, and in this lecture or in this chapter we will try to solve a differential equation, and this differential equation should be linear homogeneous differential equation, which has the general general form as given here, that is p0x d2y by dx square plus p1x dy by dx plus p2x into y is equal to 0. Here p0x, p1 and p2, these are functions of x or maybe constants, and ekhane y is to be expressed in the form of x, and this y can be expressed as the ascending or descending power of x. So and our aim will be to express y as a function of as ascending or descending power of x, and to know about how to express y in terms of x as ascending or descending power, we have to recapitulate some to solve some differential equation. Here a differential equation is given. It is a very simple ordinary differential equation, and we are very familiar to solve this type of differential equation. To solve this differential equation d2y by dx square minus y is equal to 0, we first take y is equal to mx as the trial solution, and then we find d2y by dx square. Here dy by dx first is found, and then d2y by dx square as m square e to the power mx. Now substitute this value of d2y by dx square in this equation. We have m square minus 1 e to the power mx. Remember, m is a constant, and from this equation we can find out the value of m, and here we calculate m as plus minus 1, and therefore m has two values. One is plus 1 and another is minus 1, and if we use m is equal to plus 1, then we have the solution of this differential equation as y is equal to e to the power x, and you know that e to the power x can be expressed as power of x as given here 1 plus x 1 factorial x square by 2 factorial x cube by 3 factorial etc. And another solution is for m is equal to minus 1 and is given by y is equal to minus x, and it is also expressed as this fashion, that is e to the power minus x. We know that e to the power minus x is equal to 1 minus x by 1 factorial plus x square by 2 factorial minus x is equal to 3 factorial, and so on. So we know all of these and this method and this process. And now another example is given here, which is d2y by dx square plus y is equal to 0, and here first we have to substitute y is equal to e to the power mx as in case of the first differential equation, y equal to mx, and then we in the d2y by dx square as m square e to the power mx, and then substitute these values in this equation. We have m square plus 1 into e to the power mx is equal to 0, and then m square plus 1 is equal to 0. And remember that this equation, and in the previous case this equation m square minus 1 is equal to 0, is actually called the auxiliary equation. Now solving this auxiliary equation, we have two values of m, one is plus I and other is minus I. And then the solution of this equation becomes y is equal to sin x, that is equal to x minus x cubed by 3 factorial plus x cubed by 5 factorial minus x to the 7 by 7 factorial and so on. And another solution is y is equal to cos x, that is equal to 1 minus x square by 2 factorial, x 4 by x 4 factorial minus x to the 6 by 6 factorial and so on. That is, these two differential equations can be expressed as the power of x. So the power series solution of these two equations is possible. However, this process, that is to solve a differential equation for a variable, say it is y, in terms of the power series of another variable, that is x, cannot be applied for all types of differential equation, and that can be clear from the following example. Say the given equation is x squared into y by dx squared plus x squared minus x dy by dx plus 2y, and this equation has to be solved. To solve this equation, we consider that y can be expressed in the ascending or descending power of x, and say that is here it is ascending power, it is ascending power of x. So y is equal to a0 plus a1x plus a2x square plus a3x cube plus etc., where a0, a1, a2, a3 are constants. And now solving this equation, if you try to solve this equation, we will see that all the constants, that is a0, that is equal to a2, that is equal to a3, etc., all the constants are 0. If all these constants become 0, then there will be no solution actually. There will be no solution of y. Therefore, one needs to first test whether the given equation, differential equation, can be solved in power series method or not. And the process or the method by means of which we can test whether a given differential equation can be expressed in power series method is called the Frobenius-Fuchs theorem. And using Frobenius-Fuchs theorem, we can easily understand whether a given differential equation can be expressed in power series method or not. Here we have discussed in this section the validity of power series method, and then Frobenius method. Then we will discuss about the Frobenius-Fuchs method. So first we remember or recapitulate the general form of the linear homogeneous equation, which was discussed earlier of this lecture, which has the form p0 x d2y by dx square plus p1x dy by dx plus p2x into y is equal to 0. And you know that here p0x or p1x or p2x are constants of x or function of x. And now rearranging this equation, that is equation number 1, we have d2y by dx square plus p1 by p0, p1 by p0 x, and then dy by dx into plus p2 x by p0 x into y is equal to 0. And this equation can further be expressed as d2y by dx square plus capital X1 function of x, that is here capital X1 is nothing but p1x by p0x, and dy by dx, and then capital X2 function of x into y, where x2, capital X2 is nothing but p2 x by p0x. So we denoted here another two variables, capital X1 and capital X2, and they are a function of p1, p2, and p0. So now we have to consider the following points. Which are these? These are, number 1, say for a certain value of x, which is let's say it is x, a. So for a certain value of x, say it is a, the value of p0x not is equal to 0, it does not become 0, then the equation given, that is this equation, will have an ordinary point at x equal to a. That means you have to test whether p0x is equal to 0 or not for a certain value of x, that is, say it is a. So if p0x is not equal to 0 for the value of x at a, then this equation is said to have a singular to have an ordinary point at x is equal to a. If, however, the value of p0x at a becomes 0, then this equation is said to have a singular point. So here we understand what the conditions of ordinary and singular points. So that means when the value of p0x for a certain value of x at that is a is not equal to, then the given equation or the differential equation will have um, an ordinary point at x equal to a. And if, however, p0x is equal to 0 for x equal to a, then this equation will have a singular point. Now, if a given differential equation it has an ordinary point, then it is easily soluble, or it can be solved in power series method. However, if a given equation has a singularity for a certain value of x, then it cannot easily solve. It cannot be solved in power series method. But it is not true at all. This equation can be solved even it has a singular point, but you have to consider the following points. Which are these? These are here given at the last of this lecture, which is that is given here. So here it is written clearly that, remember, for an ordinary point, Gauss solution is possible. However, if the given equation has singularity at x equal to a, the solution in Gauss can also still be possible, can still be developed. But you have to find out the following two terms, which are these are x minus a into capital X1 and x minus a whole square into capital X2. And these two terms at x equal to a should be analytic and they should have finite values. If these values, the values of these two terms, that is x minus a into x1 at x equal to a, or x minus a the whole square into x2, these two terms, any one of these two terms becomes infinite for a x equal to a, then the power series solution cannot be possible. If, however, these two terms have finite values, that is x equal to a, then the power series solution is possible. That means if a given function has a singularity at x equal to a, then the power series solution still be possible. And you have to remember that these two terms, x minus a into x1 and x minus a whole square into x2, these two terms should be finite. If, however, these two terms is not finite, it becomes infinite, then solution is not possible. Now, if at x equal to a, both of x minus a into x1 and x minus a whole square into x2, these two terms are finite, then on the point x equal to a is termed as regular singularity or non-essential singularity. If, however, x minus a into x1 and x minus a whole square into x2, these two terms becomes infinite at x equal to a, then a is said to be irregular, an irregular singularity or essential singularity. So here we understand. Here we able to know the types of singularity, and we here understand that two types of singularity is there. Number one is a regular singularity or a non-essential singularity, and number two is irregular singularity or essential singularity. And the regular singularity or essential or irregular singularity actually depends on the two terms, which are x minus a into x1 and x minus a whole square into x2. and here the condition of analytic of a function is given here. A function fx is said to be analytic or regular at a point A if the function is single valued, having derivatives of all orders at the point, so that its Taylor expansion about A, that is sum over fn A in factorial into x minus a to the power n, exists and converges to fx in some open interval, say it is b less than a less than c. Now we come to our to here. Here we come here validity and yes. So here we understand ordinary point and singular points. Ordinary point, if a function has ordinary point, then it is easily can be expressed in power series method. And however, if it is not, it has not an ordinary point, and if there is a singular point, then we have to test whether the value of whether it is a regular singular point or irregular singular point. If regular singular point is obtained, then solution is possible, and if however the point A is an irregular singular point, then the solution is not possible. And now for Venus-Push method, we come here Venus-Push method, and since whether a function, whether a given differential equation can be expressed in terms of power series method or not, or the process how to express in power series method can be understand from Venus-Push theorem. And the Venus-Push theorem to solve differential equation in power series method are given here, are follows here. If x is equal to a is the ordinary point of a linear homogeneous equation, which is given here, which is given by this equation. Okay, if this equation has an ordinary point at x equal to a, then it can be expressed as follows: y is equal to a0 plus a1 x minus a, and expressed about the point a. Y is equal to a0 plus a1 x minus a plus a2 x minus a whole square plus etc. That is, it is ascending power of x, where a0, a1, a2 are the constants. And when x equal to a is a regular or non-essential singular point, at least one of the solution can be expressed. So if the given equation has a regular or non-essential singular point at x equal to a, then at least one of the solution can be expressed as y is equal to x minus a to the power m a0 plus a1 x minus a plus a2 x minus 2 the whole square, x minus 2 whole square plus etc. So at least one solution can be expressed in this fashion, and after that the series given here 2 and here 3 are convergent at every point within the circle of convergent at the point x equal to a, and a series solution is valid if the series is convergent. It is most important. The series solution is possible if the series is convergent. So now we come for some example checking to check the singularity of some given equation. Here first, here this equation is given here, this type of equation, and we know that this is linear homogeneous equation, and we have to solve this equation in power series method. To solve this equation in power series method, we have to first check where the singularity of this point, whether that means for certain value of x, whether this equation has an ordinary point or singular points, and if singular point is there, then which kind of a singular point is that? That means whether it is an ordinary point or ordinary singular point, or whether it is regular singular point or irregular singular point. To do this, first we rearrange this equation. No, it needs not to rearrange. Here it is simple. Equation is given. It is here. So we just compare this equation to the general form of the linear homogeneous equation, that is d2y by dx square plus capital X1 into x dy by dx, and x2 function of x is equal to y equal to 0, and it is clear here that in this case p0 here this term is multiplied by p0 function of x, and here p0x is nothing but 1, and this is p1x, that is p1x is equal to x, and here this term x square plus 2 is the p2x, that is p2x is equal x square plus 2. So capital X1 is equal to P1x by P0x, where P1x is also here written here, P0x is equal to 1, and P1x is here written equal to P1x is equal to actually x, so x1 is equal to x by 1, that is equal to x, and then capital X2, that is equal to P2, this is P2x by P1x, that is equal to x square plus 2. Now if we use the value of x at as 0, then we easily can understand that P0 at x equal to 0 is equal to 1. So P0 x not is equal to 0 at the value x is equal to 0. So x equal to 0 is an ordinary point of the given equation, and this equation is therefore can easily be solved in power series method, and this equation has no singularity. Then come to another equation, and then how can it be expressed in power series method? It can be expressed in power series method as y is equal to a0 is 1x plus a2x square plus 3x cube plus data data here, because in this case a is equal to 0. So in previous case, according to Fabinus-Puig method, y can be expressed as in this fashion: a0 plus a1x minus a plus a2x minus a whole square plus etc. So here x is equal to, here a is equal to 0, so it should be a0 plus a1x plus a2x square plus a3x cube and so on. That is uh, that is that is ascending power of x can be expressed in this fashion, where all the a0, a1, a2, a3, etc. are non-zero. That is, it can be expressed as sum over a x to the power k plus r, where r not is equal, a r not is equal to 0. Now come to another example. Here the given equation is d2y by dx square plus y by x cube is equal to 0. Now rearranging this equation, we obtain x cube d2y by dx square plus y is equal to 0, and we denote it as equation number 1. So comparing this equation to the general form of linear homogeneous equation, that is P0 d2y by dx square plus P1 into dy by dx plus P2 into y is equal to 0, we can easily understand that P0 function of x is equal to x cube, and P1x here P1x is absent here, so P1x is equal to 0 and P2x is equal to from here 1, and then capital X1, that should be P1x by P0x, that is equal to 0. It is here written here 0, and capital X2 function of x is equal to P2x by P0x, that means 1 by x cube. Now for the value x is equal to 0, we have to find out, and we are trying to find out P0x. So at x equal to 0, we here find out the value of P0x. So P0x at x equal to 0 is equal to 0. Therefore, the given equation has singularity. As it is equal to 0 at x equal to 0, so it has singularity. This equation has singularity at x equal to 0. If it would not, if it was not 0, or it would not be 0, and it would have some certain values, finite values, then at x equal to 0 we will have ordinary point, but in this case we find a singular point at x equal to 0. So to express this equation in power series method, we now have to check whether at this point, that is x equal to 0, is a regular singular or non-essential singular point, or irregular singular or essential singular point. So which kind of singular point is this? We have now to find out. Then to do this, but here it is written that to check whether this singular point is regular or not essential, or irregular or essential. To do this, we first find out. We have to find out x minus a for the value of x into a. Here a is equal to 0, so it would be x minus 0 into x1 at x equal to 0, and we have to find out this value. that is equal to x minus 0 into x1. The value of what is the value of x1? X1 is equal to 0. So we write here at x equal to 0. So it is equal to 0 and this is a finite value. And then x minus 0, that is what was the formula? The formula was, the condition was x minus a whole square into x2 at x is equal to a. Here x is equal to 0. So we just use x equal to 0 here. A equal to 0, sorry. So x minus 0 whole square into x2 at x equal to 0, that is equal to x square into the value of x2. The value of x2 is written here 1 by x cube, that is 1 by x at x equal to, and if we use the value of x equal to 0, it has the value infinity. So this first value, this term has finite value, but this term has infinite value. So the condition was both of these two terms should have finite values. If any one of these two terms is infinite, then the point would be irregular singular point, and then the possible solution is not possible. So the singular point at x equal to 0 is an irregular or essential singular point. Therefore, power series method will not be workable in this kind of equation. Now another example, d2y by dx plus 1 by x dy by dx minus 1 by x square into y is equal to 0. Now rearranging this equation, we have x square d2y by dx square plus x dy by dx minus y is equal to 0, and you can easily understand that p0, to compare this equation with the general form of the linear homogeneous equation, we will have p0 x equal to x square and p1 x is equal to x and p2 x is equal to minus 1. So to check the singularity of this equation, you consider that for x is equal to 0, the value of p0x, it is given here, is equal to 0. That means x equal to 0 is a singular point. If once you get the singularity of this equation, then you have to check whether it is regular or irregular. Now to check whether it is regular or irregular, first come to here that to find out the value of capital X function of x, that is equal to p1x by p0x. Now substitute the value of p1x. P1x is given here x and p0x is equal to x square. So p1x by p0x is equal to 1 by x, and capital X2 function of x is equal to p2x by p0x, that is equal to p2 is equal to minus 1 and p0 is equal to x square. So it is minus 1 by x square. And now, so for the value of x is equal to 0 on the term x minus a is equal here 0. So x minus 0 into x1 at x equal to 0, that is equal to x into x1 is equal to here 1 by x at x equal to 0, that is equal to 1, and it is finite one. And then x minus a whole square into x2 at x equal to 0, that is equal to x square into minus, here we already obtained the value of x2. So substitute this in this here, minus 1 by x square at x equal to 0, that is equal to minus 1. So it is also a finite value. So both of this term and this term have finite values. So the power series method is workable in this case, and this equation can be expressed in power series method, and the point x equal to a is a regular singular point or non-essential singular point of the equation given by these equation number is given by this. Okay. Now another example which is given, it is different from the previous ones, but have similarity with the general form of the linear homogeneous equation. Here the given equation, we consider that 1 minus x square d2y by dx square minus 2x dy by dx plus n into n plus 1 into y is equal to 0. So if you arrange this equation or consider compare this equation with the general form of the linear homogeneous equation, that is p0 d2y by dx square minus plus p1x dy by dx plus p2x y is equal to 0, as since you have already understood that this value p0 or p1 or p2, this may be a function of x or may be constant. So it is their constant, p2 is equal to constant. So p0x from this equation we can easily find out the value of P0 x, that is equal to 1 minus x square, P1 x is equal to minus 2x, and P2 x is equal to n into n plus 1. So capital X1 is equal to P1x by P0x, that is equal to minus 2x by 1 minus x square, and capital X2 is equal to P2x by P0x, that is equal to n into n plus 1 by 1 minus x square. Now look at this. Look at this. P0 x is equal to 1 minus x whole square. If x is plus minus 1, there P0 function of x is equal to 0. That means at x is equal to plus minus 1, P0 x is equal to 0. That means, or from this you can conclude that x is equal to plus minus 1. These two values, that is plus 1 and minus 1, are the singular points since P0 x is equal to 0. Singular point of the given equation. Now, whether this equation can be expressed in power series method or not can be understood by checking whether x is equal to plus minus 1, that is plus 1 and minus 1 are these two values are regular singular point or not. If it is regular, they are regular singular points, then the solution is possible. So here come here check the values x minus what was the condition, x minus a into x1 at x equal to a, and x minus a whole square into x2 at x equal to a, and these two terms we have to find out these two terms. Here we found that x is equal to 1 here. So x minus 1 into x1 at x equal to a is equal to x minus 1 into you substitute here the value of x1. The value of x1 was minus 2x here, minus 2x by 1 minus x square at x equal to plus 1. That is equal to, it can be written as 1 minus x, negative sign, and here another negative sign will come and which will become positive. So 1 minus x into 2x by 1 minus x square at x equal to a, and that is equal to you can express this term as 1 plus x and 1 minus x. So 1 minus 1 minus x will cancel out and it will give 2x by 1 plus x at x equal to 1, and use the value of x equal to 1. You will have 2 here, 2, and here also 2, that is equal to 1. That means this value x minus 1 into x1 at x equal to 1 is finite. Now come to the second term, that is 1 x minus 1 whole square into x2 at x equal to 1. That is equal to, it can be written as 1 minus x whole square into the value, write the value here, substitute the value of x2 was n into n plus 1 by 1 minus x square. We use here n into n plus 1 by 1 minus x square, and that is equal to, it can be, which this term can be expressed as 1 plus x and 1 minus x, 1 minus x and another, and one term of 1 minus x will cancel out from these two, and you will have 1 minus x by 1 plus x into n plus 1, and if you use the value of x equal to 1, then it will give 0. So it is also a finite value. Therefore, at x equal to plus 1, the given equation has a regular singular or non-essential singular point, and therefore it can be expressed in terms of power series method. Now another value, which was x is equal to minus 1, and now we have to check for x minus 1. Here we use the value of x as minus 1 as, so what was the condition? That was x minus a into x1 at x equal to a. So here a is equal to minus 1. So x minus or minus 1 into x1 at x is equal to minus 1, that is equal to x plus 1 into, we know that x1, we have x1 as minus 2x by 1 minus x square. So from these we have minus 2x, and from these two term 1 plus x will cancel out, and then we get minus 2x by 1 minus x, and using the value of x is equal to minus 1, we have x is equal to minus 1, we have here 2 from here and 2 from here, that is equal to plus 1. Plus 1. So no, it is minus 2, yeah, plus 1. So it is finite. and then the value of this term, that is x minus of a whole square into x to x is equal to a. Here already we have seen that a is equal to minus 1, so it is x plus 1 whole square into x2, that is equal to 1 plus x whole square into n into n plus 1 by 1 minus x square, that is equal to 1 plus x, one term of 1 plus x to cancel out with one term of this term, so that it will give 1 plus x by 1 minus x into n plus 1, that is equal to 0, and it is a finite value. So at x is equal to minus 1 is also a regular singular or non-essential singular point, and the Cauchy solution can be possible. So Cauchy solution for two values x is equal to plus 1 and x is equal to minus 1 can be possible. So you have to test another some other equations, whether those equations can be expressed in Cauchy's method or not. So this is the first lecture, and after that we will go the next. We will go the next topics. So today it is the lecture is finished here.